Hello and welcome to Talk of Today, where we explore developments in science, technology, and society, and what they could mean for the future. I'm your host, Sam Barton. So there are just a couple of things I want to mention before I get onto the show. Firstly, the Chrome extension Life tab that I've been working on is available. It is basically a digital productivity planner and data tracker that helps you keep on task and track things that you think are important to help you live a more informed life. The reason why I decided to make it is because there is not a single productivity planner or journal or diary, anything that I've ever stuck with. So I took the things that I liked about all the ones that I have used and I threw them together to make this what is currently available is just a proof of concept, but I've actually stuck with it, and I think that's because it pops up every time I open up a new tab. So instead of actually having to actively remember to find out what I need to do, instead when I hit Command T, Control T to open up a new tab, this pops up saying, "Hey dude, you've got some stuff to do," and it's actually made me more productive, but I am biased, so I invite you to go and check it out. You can do that at just type in LifeTab into the Chrome extension store, or you could head to Talk of Today, and there are links to it there. The version that is online currently is a proof of concept. Over the next few weeks and months, we're going to be releasing updates that include cloud integration. There is a data tracking feature there. What's coming is the ability for you to enter fields, different types of data that you do want to track. So it could be, your blood sugar, or did you walk the dog, basically whatever you want, and then give you the ability to derive insights from that data over time and see it visualized. So some simple ones could be, how does your coffee consumption relates or correlate with the amount of sleep that you get, or how does your productivity or number of tasks that you don't get done a day, how does that coincide or correlate with your meditation practice perhaps. So this is in a way a productivity tool and a data tracking tool for biohackers. So if that sounds like you, or if you are just interested, I invite you to check it out. And your feedback is really, really welcomed and sought after. Because we're at the initial stages, anything that you say or any feedback that you give could result in new features or whatever being implemented. So the way to think about it is you could be creating or help create the productivity planner that you want to use. So I really, really, if you're really interested, please check it out and get in touch because, well, I'm excited. Anyway, on to the show. The meaning of life is to live forever. At least, this is what Google's artificial intelligence chatbot responded with when asked the greatest existential question just a few years ago. Some may think of this as fundamentally wrong, violating some unwritten but implicit law of the universe. But isn't avoiding death the most natural thing in the world? We are the products of over 1 billion years of evolution, and at each step, our ancestors have been trying to avoid death and procreate. In our lives, the prospect of getting older and dying is seen to be an eventuality, and for good reasons. But there are some in the world who see the inevitable degradation of the body as just a biological engineering problem, and one that can be solved. My guest today, Aubrey de Grey, is one of these people. He's a British medical gerontologist, chief scientist and founder of the SENS Research Foundation, an institution focused on using regenerative medicines to repair damage underlying the diseases of aging. Aubrey has been on a crusade against aging for decades. In that time, we've made significant progress. So much so that Aubrey claims that the first person to live to 1,000 is alive today. Some optimistic estimates state that we may solve this age-old problem by as early as 2030, with other estimates spanning a few decades. It's not a question of if, but when. And when it is indeed possible to forestall death seemingly indefinitely, what then? Will there be a moral imperative to make these technologies available to everyone on Earth? I think so. Though, to be honest, it seems a bit absurd to say that, in a world where we can't even guarantee everyone on Earth the basic conditions for life. These technologies will give us the freedom to explore the world and its beauty indefinitely, having the choice to embark upon the greatest adventure of all, death, will be one that I think people will demand control over. The contentious issue of euthanasia may see resolution. These are just some of the moral quandaries we are likely to be faced as these technologies develop, and we need to be discussing them now. I've been following Aubrey's work for a number of years, and I was extremely excited to have him on the show. In our conversation, we talk about how he got involved in the industry, a bit of science involved, and what things will look like moving forward. And because right now you can't live forever and your time is precious, I will get on to the show. So please enjoy my conversation with Dr. Aubrey de Grey.
My name is Dr. Aubrey de Grey, and I'm the Chief Science Officer of Sense Research Foundation. We are a biomedical research charity based in Silicon Valley, California, and we are focused, of course, on doing something about aging. When I say something, of course, I actually mean we're focused on developing medicines that will bring aging under truly comprehensive medical control. In other words, the same kind of control that we have currently in the developed world over most infections. And we believe we can do this by a variety of different techniques that essentially involve the repair of the molecular and cellular damage that the body does to itself throughout life. A few of these techniques are well understood and worked on by other people already, but most of them are not, and that's why we exist.
And how did you get involved in, I'd say, anti-aging research?
I got involved basically because in my mid to late 20s, I made the horrifying discovery that most biologists were not very interested in aging. I had gone through my life blissfully unaware of this and thinking that biologists in general understood, like me, that aging was by far the biggest problem for humanity, and that they would therefore be working on trying to do something about it. And when I discovered that that wasn't the case, I decided, well, I'd better switch fields. I was previously working in artificial intelligence research, also for humanitarian reasons, but this was clearly an even more important problem.
I've heard you describe aging as the world's most important problem, and some may understand that or understand the reasoning behind that without much of an issue, but for those who don't, could you unpack it a little bit?
Sure. I mean, to me, it's all about how much suffering something causes. Suffering is what we're supposed to do something about. I'm not just talking from like Holy Scripture or anything. I'm talking just like people just don't like to see each other suffer, and I don't like to see people suffer either. So I think that's what makes suffering the thing that we should be working as best we can to minimize. And aging causes far, far more suffering than anything else. It's the source of 90% of the ill health in the industrialized world, probably more than 70% at this point of the ill health in the world overall. And of course, ill health is the major source of suffering. Now, if you ask anyone what they value most in their life, they'll probably say their health.
In one of your TED Talks, you refer to a table or a chart with basically a list of diseases on there, and you highlight the necessity or why it's important to distinguish between the ages relating to the diseases relating to aging and the others. Do you mind expanding upon that?
That's right. I think the classification that you're referring to is, I basically try to answer the question, what are the ways in which people can get sick? And I basically break it down into four different types of sickness. There's infections, there's congenital diseases that we inherit, there are the chronic progressive diseases of old age, and there is aging itself. And this is not controversial, but what is controversial is the assertion that aging itself is actually pretty much indistinguishable from the diseases of old age. Whereas, by contrast, the diseases of old age are nothing like infections. They cannot be cured in the same way that an infection can. And the misconception that is so prevalent in the world with regard to these similarities and dissimilarities has led to the misallocation of billions and billions of dollars of medical research funding and medical funding, and it continues to do so. And that's what the whole field of gerontology tries to correct. And in particular, the work that we do tries to correct it in a manner that will actually deliver therapies that really work in the foreseeable future.
Just out of curiosity, how much money does the field of gerontology get all around the world? And as a percentage of the whole, how much is it?
Well, I don't know the precise numbers for the whole world, but I have a reasonably accurate understanding of the numbers for the USA, and I think they are representative of pretty much all industrialized countries. In the USA, their main provider of funding for medical research is the National Institutes of Health, a branch of the government, of course. They provide something in the region of $30 to $35 billion a year. About 3% of that goes to a component of the NIH called the National Institute on Aging, but unfortunately only about 15% of the money within that entity goes to research on the biology of aging, as opposed to social gerontology or geriatrics or whatever. And within that
could be spent.
And within that, I'm not done, I'm afraid. And within that, the overwhelming majority is spent on trying to understand aging better, but without any particular priority to anything translational. In other words, doing anything about aging. If you look at how much is actually spent on translational, what you might call biomedical gerontology, it's probably no more than $10 or $15 million per year, which is, pathetic.
Yes, it's a drop in the ocean. That's nothing. Some people could blink and, produce that sort of money. That's quite a shame.
Oh, yeah.
So when talking about dealing with the issue of aging, you say that the best way to solve this issue is to maintain the body, not to come in at the end and try and fix the issues of, decades and decades of degradation, but to maintain the body as it is when it's, fully functioning. And there are 7 ways that this can happen, and you describe them as the 7 deadly sins. Is that right?
7 deadly things, that's right. Strategies for engineered negligible senescence, but you don't need to remember that part.
Okay.
Yeah, I mean, basically the idea that we need to be more preventative is not new. That's the idea that really gave rise to the whole field of gerontology more than a century ago. The problem is that until I came along, gerontologists were taking that idea too far. They were saying that what we need to do is somehow clean up metabolism, make our bodies create damage at a slower rate than they normally would. And the inspiration for this, of course, was the fact that we do see a lot of variation in the natural world in the rate at which different species create damage and actually the rate at which they age. However, it turns out that our metabolism is so insanely complicated that it's basically impossible to tweak it so as to slow the damage creation down. And so what I realized, and what I've been promoting all this time, and what is now increasingly acknowledged as a realistic approach, is to kind of go halfway to there. In other words, not try to slow down the rate at which damage is created, but yet still to repair the damage before there's so much of it that you get sick.
Yeah. Well, and what are these 7 deadly sins, or the realities of this? You don't have to go into too much detail, but if you could just give some examples of the processes.
Yes, I can do it pretty quickly. Of course, there are many, many, many different types of damage. What there are 7 of is categories of damage, each of which can be addressed, can be repaired by some generic therapy. So one example is the loss of cells just dying and not being automatically replaced by the division of other cells. And of course, the way to fix that is to put cells back, and that's what stem cell therapy is. To program cells in the laboratory in such a way that you can inject them into the body and they will divide and transform themselves into replacements for the cells that the body is not replacing on its own. Then there are other types of damage that involve molecular waste products accumulating. And there we can introduce either there are in some cases we can introduce tweaks to the immune system so that the immune system will break these things down. Sometimes we have to go a little bit more creative and introduce new enzymes identified in other species, especially in bacteria, which have degradation capacities that we don't naturally have at all. That kind of thing.
Some people might say that we're playing God and that death is a necessary part of life. And I'd just like to hear your thoughts on this, because I was reading Richard Dawkins's well-known book, The Selfish Gene, earlier on this year, and he says that the issues of aging are kind of genetic baggage. They're not necessary. It's just that we've kind of accumulated them, and because we reproduce decades before death due to aging occurs, the deleterious genes responsible for aging still propagate. What are your thoughts on that?
That's absolutely correct, and indeed it's generally understood. There is only a very small minority of biologists now who believe that aging exists for some kind of evolutionary purpose. Most people recognize that evolution just hasn't taken the trouble to complete the job of eliminating aging. In other words, every living organism only lives as long as it does because of carrying around a great deal of inbuilt anti-aging machinery, and the reason we age is because that anti-aging machinery is not 100% comprehensive.
So what sort of progress are we making at the moment? What sort of or have any leaps and bounds been made in this field in the recent years?
Oh yeah, absolutely. I think we're now in a position where we can say that everything that needs to move forward is actually moving forward. The only area that was really in good shape when I came along and started to try to do this was stem cell therapy, which was widely understood to be something that had great medical applicability across the board, not just in aging. But the approaches that I put forward, or that I kind of brought together for addressing the other types of damage that we accumulate during life, were at a very much earlier stage in terms of their development and also in terms of their appreciation by the medical community, the medical research community. So we were starting from a very early stage, and that's why we created Sense Research Foundation as a non-profit, actually, because these things were just far too early to be commercializable, to be investable. However, at this point, that's only partly true now. Some of these things we have successfully brought forward to the point where we have been able to spin them out into startup companies, and where they may be in clinical trials within a year or two. So,
sorry, I was just going to say I remember hearing some news a year or two ago about Elizabeth Parrish at BioViva. Did she successfully lengthen? Did they successfully lengthen her telomeres using some genetic engineering techniques or something of that nature?
So I know Liz quite well, but I haven't been in touch with her in the recent past, and I don't know for sure the details. I haven't seen the data that's been generated from the tests that have been done on her. It's obviously, something to pay attention to. Whether it's got much scientific value in itself, being just one patient is debatable. But at the same time, the championing of self-experimentation is something that I do very much approve of. I think it's a tradition that has existed a very long time and got a great deal of distinguished history. But it's it really is a great way to highlight and to raise the profile of this kind of work. And so, we hope obviously that she's not doing anything that will be harmful and risky. And some people say that it is. But I think all in all, she's doing a good deal more good than harm with the work that she's doing.
Mm-hmm. And could you just explain briefly what a telomere is and what is the Hayflick limit and all this sort of stuff?
Sure. So our DNA is packed into these chromosomes, which are molecules of just really long molecules or strings of these things called nucleotides. And the strings obviously have ends, like any string. Now, the ends actually are a problem because chromosomes break every so often, just spontaneously as a result of damage from this or that source. And the cell needs to stitch those chromosomes together again after they've broken. But that means, of course, that the machinery that stitches broken chromosomes together needs to be able to identify the end of the chromosome so that it doesn't join two chromosomes together that are perfectly intact. That causes a hell of a lot of problems. So at the end of the chromosomes, we have these special sequences that are treated very specially and are protected from being joined together. Those are the telomeres. Now, there's a problem, however, with DNA, which is that when you copy it, when you replicate it, the machinery that replicates it is not able to replicate right to the end of the chromosome. So the chromosome gets a little bit shorter each time the cell divides. And if you make cells divide a lot, then the cumulative shortening that happens is so substantial that this special sequence, the telomere sequence, goes away. And of course, then, as I mentioned, chromosomes get accidentally joined together end to end and so on. Right. Now, of course, something's got to be done about this because cells have to divide in the body. And sure enough, evolution has invented an enzyme called telomerase, which adds additional DNA of this special sequence on the end of the chromosomes to compensate for the shortening that happens during cell division. But that enzyme telomerase is only synthesized, it's only expressed, as biologists call it, in a small number of cells and at a very low level. And the reason for that is because the lack of expression of telomerase is a fantastic defense against cancer. It means that if a cell gets into a state where it wants to divide and divide and divide even though it shouldn't, eventually it'll stop dividing just because of this shortening of the telomeres. Works really well. It doesn't work perfectly, of course, or if it did, we wouldn't die of cancer, but it works very well. So the problem is, of course, that this means there's a trade-off. Some of the cells in the body do need to divide a reasonable amount, and they don't express any telomerase, or only express very trace amounts. And so the telomeres do get slowly shorted during life. And in some cases, it may be that process causes problems of its own as a kind of trade-off against the problem of cancer.
Can you talk a little bit about senescence and senescent cells?
Sure. So actually, senescence was the term that Leonard Hayflick, the person who discovered this problem of finite cell division capacity that I just described, that was the name that he gave to this phenomenon. And it was a bit of a misnomer, to be honest, because it implies that it's got something to do with aging in a living organism. And as I said, there may be certain situations in which this phenomenon does have to do with aging in a living organism, but Len certainly didn't show that. Because what he did was he took cells out of the body that don't normally divide very much, and therefore they can perfectly well get away without expressing any of this enzyme telomerase. The thing is that even though they don't normally divide very much, if you do the right thing to them, you can make them divide like crazy forever and ever until they can't anymore. And that was what he discovered. But it wasn't a physiological phenomenon because the type of cell he was using doesn't normally need to divide much. All right, but however, it turns out that senescent cells do actually occur in the body in a different way. They can actually occur as a result of other types of DNA damage that are not done necessarily as a result of the shortening of the ends of the chromosomes. And the reason we call those by the same name is because they have the same kind of behavior. They express the same proteins, they get into the same kind of weird state, and it turns out that those cells are quite bad for us, or at least people have good evidence that they probably are bad for us. These cells are capable of secreting nasty proteins that that will promote the carcinogenicity of cells nearby. And so these cells are a problem, and we need to get rid of them. Now, it turns out that the immune system does get rid of them reasonably well, but it doesn't get rid of them perfectly. A few of them carry on and accumulate during life. And actually, one of the projects that we've recently initiated is looking at trying to improve and enhance the ability of the immune system to eliminate these cells better than it naturally does.
I think I saw something earlier on last year. A team genetically engineered some mice so that when some of their cells went senescent, some sort of marker was produced, and that caused, basically like the cleanup crew to come in and get rid of them before they could cause too much damage to the cells around them. Does that ring any bells, or does that sound about right to you? and I think it
much.
increased the life expectancy of these mice by 20%, which is
It was okay.
substantial.
So it's a little bit more complicated than that. So the initial work that you're referring to was actually done now 6 years ago at the Mayo Clinic in Rochester, Minnesota, and basically the work was to first create mice that made senescent cells at a very rapid rate, much more rapidly than any other aspect of their aging. So they lived an unusually short lifespan as a result of this very accelerated accumulation of these cells. And they engineered these mice so that not only did they make these cells very rapidly, but also they could be given a drug that would do exactly what you said. They would get rid of these cells. And that was very interesting. It alleviated the accelerated aging phenotypes that the mice had. So everyone got very excited, and a company was formed, and it got lots of money, and it's moving forward quite well. They now have data that show that the same kind of thing does indeed, as you say, have beneficial effects, less dramatic, but still beneficial effects in normal mice. There's still a lot of work to do to know whether this is going to have much effect in the clinic, but obviously that's the direction that they're going in.
Okay, well, thank you for clearing that up. It's still exciting nonetheless. So you speak of the longevity escape velocity. Do you mind just explaining what that is?
Sure. So we are, as I have explained, talking here about therapies that will, in the foreseeable future, repair a variety of different types of damage that the body progressively does to itself. Now, if you think what that means, it means that the therapies can be applied repeatedly, and they can, in principle, keep the amount of damage that the body is carrying around down to a very tolerable level, indefinitely. There's one problem with that, which is that we don't expect the therapies that repair damage to be perfect out of the gate. We expect that just as aging exists as kind of the gaps in our natural evolved anti-aging machinery, similarly, when we plug some of those gaps, we won't plug all the gaps 100% perfectly at first. So what will happen is that, as a result, initially the damage will accumulate more slowly, but the types of damage that accumulate will be more difficult to repair than the ones that we initially succeed in fixing. And that means that we need to improve the therapies eventually. So the term longevity escape velocity is what I coined to refer to the rate at which we need to carry on improving these rejuvenation therapies following the point where we get a kind of version 1.0 going in maybe 20 or 25 years from now. The good news is that that's going to be well within what we can do. If you do any kind of arithmetic on this, it seems basically certain that the rate at which we will need to carry on improving the therapies will be a tiny fraction of the rate at which technologies normally improve.
Okay. So some people people make predictions about this sort of stuff all the time, and I've heard Ray Kurzweil's prediction saying that by 2029 we will have solved the issue of aging, and I think you've said that the first person to live to 1,000 is alive today. Do you stand by these or do you stand by Ray Kurzweil's prediction, or do you truly believe that the first person to live to 1,000 could be alive today?
I certainly do, yes. Ray is probably slightly more optimistic than me in terms of time frames, but only slightly. Essentially, I think that if we can achieve this first generation of rejuvenation therapies within the next 20 or so years, which I think we have a 50% chance or so of doing, just so long as the work is reasonably well funded, then we're done, basically. We will achieve and maintain longevity escape velocity, and that means that however old someone gets, they will never exhibit the ill health of old age in any way. And that means, therefore, that they won't exhibit the mortality rate associated with old age. So if we look at how often people die when they're young, we can just do the arithmetic. We can say, well, okay, supposing someone reaches their 26th birthday, what is their probability of not reaching their 27th birthday in a typical Western country today? And the answer is less than 1 in 1,000. So you can do the arithmetic. People who are going to benefit from longevity escape velocity will, as things stand, on average, live that kind of distance. Of course, only on average, some people will get hit by trucks. Maybe the Earth will get hit by an asteroid. Anything could happen, but that's the logic.
Yeah, well, it's having looked at your work over the past few years, I actually view the world, and I'm living my life in such a way that I think that I will live that long, and it's guiding the decisions that I make. So I thought I'd let you know, because I think there are a lot of people out there who are thinking along the same lines. It's quite exciting. It's a very exciting prospect, and to the people who, I guess we have the freedom to want to live for as long as we should have the freedom to live for as long as we want, and then have the freedom to call it quits and say, you know what, it's time for the ultimate adventure. But I think delivering that freedom to individuals is a powerful and very positive thing. So you're working on some incredible stuff.
Well, thank you very much for that emotion. I agree.
So I guess we'll just wrap up very shortly. I was wondering if you had any requests from the audience, or if you'd like to mention a few things before we close up.
Yeah. Sure. So, well, the first thing I'd like to mention, of course, is that the amount of information we've been able to cover today is just a tiny fraction of what we have on our website. Please go to sense.org and have a look at what we do, and sign up to our newsletter so that you can keep up to date. That's the kind of thing that we like to happen. So we have a nice big friendly donate button on the front page, and we'd love to receive.
There's no shame in that. There's no shame in that. Especially considering how little you're getting from all the governments.
And for those people who are interested in investing in companies rather than donating to charities, or perhaps doing both, obviously there are lots of opportunities. I mentioned earlier on that we've spun out a number of our projects into startup companies. That's continuing to happen. So you can always write to us and ask more about that. There's a contact form, of course, on the website.
Okay, just one more question. Is there anything that's happened in the past few months that you're just extremely excited about? It could be a development. It could be completely unrelated to aging. But what's been exciting you recently?
Well, I mean, I'm constantly excited about what's going on in our work because, of course, I'm at the coalface of it. I'm the chief science officer of the foundation, and so I'm always immersed in the details of each of the projects. And so things will excite me because I see them. I know that they are substantial steps forward, even though it would take me half an hour to explain why they're important. But yeah, I mean, basically, I think to summarize, the thing that excites me most about the past year's progress is that both of the areas of aging research of our research that were really failing to move forward have finally started to move forward in a very big way. That was, first of all, mitochondrial mutations, basically figuring out a way to sidestep what goes on there by putting backup copies of the mitochondrial DNA into the nucleus, an idea that actually originated in Australia more than 30 years ago. And secondly, the elimination of molecular crosslinks in the body that reduce the elasticity of tissues like the major arteries and cause things like hypertension. Both of those areas were really stagnant for a long, long time, and we've really been able to break through those barriers.
That's great news. That's great news. Well, Aubrey, thank you very much for being on the show. Everything, all the links, and do you mind if I link to your Twitter page and SENS and all that, of course, in the show notes?
I'd be delighted. Thank you.
Alrighty, my pleasure. And thank you very much for being on the show.
Thank you for having me.
Hey guys, I hope you enjoyed the show. What a topic. I mean, it's all well and good talking about when I say normal scientific developments, I mean, they're all pretty exciting, but nothing quite has the gravitas of, the idea of living forever, or whatever that even means. I mean, even an extra 100 years would be kind of redonkulous. I mean, think about how much we've experienced, how much progress we've experienced within the past decade alone. What's the future going to look like? We're at a point now where we can take our evolution into our own hands. And I mean that in a biological sense and from a societal standpoint. So what's the future going to look like? Are we going to split off into different species when we become a spacefaring people, or who knows what's going to be right, what's going to be wrong? Are we in need of a global ethics committee, perhaps? I don't know. All I know is that there are a number of issues, many of which are deeply morally and ethically just bizarre things that we never have really needed to contend with. And these are issues that we're going to be dealing with within a lifetime, whatever that even means now. So I don't really have any resolutions for you, but just some questions. It's an interesting time. It's an interesting time. So if you've enjoyed this episode, if you've enjoyed other episodes, please consider supporting the podcast. The Codcast. What a fishy thing to say. You can do that at talkoftoday.com/support. I'm now accepting donations through Bitcoin and Ethereum, or you can support through Patreon. You can also support the podcast by sharing this on social media or just talking about it with your friends. And any feedback is welcomed. If you like what's going on, but you think, the intro music lasts for too long or not long enough, or you think I just need to shut up and let the people speak, whatever feedback you've got, just let me know. I'd love to hear it. Also, I was going to say something. Whatever that something is, we will never find out. Yeah, and if you want to get in touch or just ask any questions, or if you have some ideas for future podcast episodes, things you might want to find out, people you think I should speak to, please just reach out and say hello. You can do that at talkoftoday.com through the contact form, or you can just send me an email at sam@talkoftoday. I'm on Twitter at Sam H. Barton, I think, or Instagram at shbarton. So reach out to me through any of those channels, and I'll happily have a chat to you about feedback or what you want from the podcast, or even just have a good old discussion about the future. So anyway, on that note, I think I will bid you farewell. Have a great morning, afternoon, drive, lunch, dinner. I hope if you're doing the laundry, if you're doing anything, enjoy it. And until next time.